Hi everyone. In this video we're going to look at heat transfer, and to do that first we're going to have a brief look back at temperature and the difference between temperature and heat. Then we're also going to have a look at some of the heat transfer mechanisms we talked about before, so conduction, convection and radiation. Then we're going to look at heat capacity of an object and try a few example questions based on that. And then finally for this video we're going to look at specific heat capacity and then try a few example questions on that too. So let's give it a go. Let's start by reminding ourselves of the difference between heat and temperature and what temperature really is. So all the matter that we talk about in the leaving cert material is divided into either a solid, a liquid or a gas. So all the stuff that surrounds you is either a solid, a liquid or a gas. In a gas, the particles are free to bounce around and move around like crazy. In a liquid, they are not able to move as freely, but they can still flow past each other and move around a bit. And in a solid, even though the particles aren't really free to move, they do vibrate. So in each of these three scenarios, the particles are able to move around or vibrate a little bit. One way to think about temperature is that it's a measurement of the average energy that these particles have. So how much are they moving around in the solid, liquid or gas? How much internal energy do they have? Heat, on the other hand, is a form of energy, so it's going to be measured in joules, and think of that as the total amount of heat energy that that body has. The temperature measures the average, the heat measurement will be the overall. So temperature is going to be measured in degrees Celsius, or else in Kelvin, and the heat is going to be measured in joules. To try to illustrate the difference, what I've got here is just a picture of a bathtub and a pot. And let's imagine that they're both filled with water at the same starting temperature, which is, let's say, about 20 degrees for room temperature. And now let's say we're going to heat them up to a bath type temperature of about 40 degrees, which is a little hot for a bath, but it'll do the job. So if we heat both of these to 40 degrees, they'll both have the same temperature. They'll both have a temperature of 40 degrees at the end of that. But it's going to take a lot more energy to heat up the bathtub than it is to heat up the pot, because you have to heat up a lot more stuff. So obviously at the end of this, the bathtub would have a lot more heat than the pot. To round off our look at temperature versus heat, let's look at the two different scales we can use for measuring temperature. We can use degrees Celsius for everyday things. So like the room temperature is usually about 20 degrees Celsius. Human body temperature is about 37.5 degrees Celsius. Water boils at 100 Celsius, freezes at 0 Celsius. For kind of everyday things, we tend to use degrees Celsius. Whereas for the most part, we should really be using Kelvin in physics. Now, Kelvin is kind of a better unit in a way because it measures from absolute zero. So we set up Celsius. That's why it's so kind of nice and neat that water freezes at 0 and boils at 100. It's because we chose that frame of reference. Whereas Kelvin is an absolute one. It's regardless of our human values. At 0 degrees Kelvin, there's no movement of particles. That's absolute zero. So you need to be able to comfortably convert between Kelvin and Celsius. And just remember that 0 degrees Celsius is 273.15 Kelvin. On the bright side, when you're measuring 1 degree Celsius, the difference between, say, 1 degree and 2 degrees is the same as between, say, 1 Kelvin and 2 Kelvin. So each unit is the same, it's just the starting points that are different. Next, let's briefly, and this time it will be brief, let's briefly recap how heat is transferred from one place to another. So the three main methods are conduction, convection, and radiation. In conduction, the heat is transferred from molecule to molecule. So if you think back to our solids, liquids, and gases diagram, this will work better for solids and liquids than it will for gases because the particles are going to be touching a lot more often. Radiation, on the other hand, doesn't need a medium to pass through. So it doesn't matter if you're talking about solids, liquids, and gases. Radiation can go through a vacuum because heat is moved by electromagnetic waves. That's how heat from the sun is able to reach us on Earth through space, even though there's no gas, solid, liquid, or gas in space. And finally, convection. So convection currents are set up when the general thing here is hot things go up, cool things go down. So when things heat up, they move around more, which means they're going to be a little bit more distant from each other, which also means that they're going to be less dense because they now take up more space. So when you heat something up, it expands, takes up more space, and therefore becomes less dense. Now, denser things tend to go down and less dense things tend to go up. So when you heat up a liquid or a gas, it'll expand, take up less space, take up more space, become less dense and go up, and the denser stuff, colder stuff will come down to replace it, setting up this convection current. Next, we're going to have a look at the idea of heat capacity. So capacity being how much something can take. You know, the capacity of bus would be how many people can get on the bus. So heat capacity is for a range of different objects. So here's just a picture of different things. So each different object here can take a different amount of heat before its temperature goes up. So each one can take a different amount of heat before its temperature goes up by 1, and this property is referred to as its heat capacity. So the heat capacity of an object is the amount of energy you need to give it to make it raise its temperature by 1 degree Celsius or 1 Kelvin. So its unit therefore is joules per Kelvin. So we're about to have a look at a couple of these calculations based on heat capacity. And just to familiarize yourself with some of the symbols we're going to use Q to represent heat energy, capital Q. We're going to use a capital C to represent the heat capacity of an object. And the last two symbols there need a little moment of explanation. The little triangle is called delta, and it refers to a change in something, so a difference. Now that'll make more sense, you understand, with the weird looking egg thing with a little line through it, that's called theta. That's usually, in our context, we're going to use it to refer to temperature. So together, that triangle and the theta refer to the change in temperature of the object. So Q for heat is going to be measured in joules, C for heat capacity is going to be measured in joules per Kelvin, and the delta theta, so the change in temperature, is going to be measured in Kelvin. Alright, let's give a couple a whirl. Now for each question, I'd like you to pause the screen when you see the question, give it a shot, and then if you move forward a couple of seconds, you see my explanation and the answer. But please make sure you try these yourself. That's how you get better at them. There's no point just skipping to me giving the answer. Please try it yourself first. Even if you make a mistake, who's going to know? Alright, let's give it a whirl. Okay, let's have a look at the first one. So always start off by just writing out which equation you're going to use. In this case, we're going to use that the energy is equal to the heat capacity of the object times the change in temperature. I want you to start thinking about this as one thing. The change in temperature is just one kind of item, for now anyway. Okay, so what are we given? We're told that the calorimeter of oil has a capacity, capital C, of 1500 joules per Kelvin. We know that we want to raise the temperature from 10 to 80 degrees Celsius. So the delta, the change in temperature, is equal to the final temperature, which is 80, minus the starting, which was 10, which works out as 70 degrees Celsius, or we could also say it 70 Kelvin. And now we have everything we need. We have the heat capacity, we have the change in temperature. Let's figure out how much energy was transferred. So Q is equal to the heat capacity, which we are given as 1500 joules per Kelvin. And we're timesing that by our change in temperature, which is 70 Kelvin. And that works out, I've calculated it before, I cheated a little, as 105,000. And let's just check our units. Kelvin by Kelvins cancel each other out, leaving us with the joules, which is a measurement of energy. So that makes sense. We should be happy enough for that first one. Okay, number two, they've given us a slight little curveball. They've given us our energy in megajoules. So they said 1 megajoule. And a megajoule is 1,000,000 joules. So that's equal to 1,000,000 joules. Now, if you're comfortable using scientific notation, that's 1 times 10 to the 6 joules. Okay, so we have our heat capacity. We have our energy. We have our heat capacity, and we're just looking for temperature. So the capacity is 600 joules per Kelvin. So let's use a formula. Q is equal to heat capacity times change in temperature. We're going to rearrange it. This time they're asking us to find the change in temperature. So let's just rearrange it a little bit. We have Q is equal to C times the change in temperature. And we're looking for the change in temperature, so let's divide both sides by C. So Q over C is equal to the change in temperature. That means 1,000,000 joules divided by the heat capacity, which is 600 joules per Kelvin. Will give us our change in temperature. That works out as 1666.7 Kelvin. So we're going to check the units. Joules divided into joules cancel each other out. And this is 1 divided by Kelvin to the minus 1. So that works out as 1 Kelvin. Question 4 is or 3 even, is a very straightforward one. We are told that the energy used is 4,000 joules, and that raises the temperature of a calorimeter of water by 10 degrees. So the change in temperature is equal to 10, and we're looking for the heat capacity of this. So we have Q is equal to the heat capacity, which is the thing we're looking for, times the change in temperature. So we're looking for C on its own. Let's divide both sides by the change in temperature. That gives us energy over the change in temperature, delta theta, is equal to our heat capacity. We know that the energy was 4,000 joules, and the change in temperature was 10 Kelvin, giving us a heat capacity of 400 joules per Kelvin. And the final concept we're going to look at in this video is the idea of specific heat capacity. So the previous thing we were looking at, heat capacity, would be how much energy was needed to raise the temperature of an object by 1 degree Celsius or Kelvin. Now that's very kind of artificial. It's like, how much would this chair go up by if you heat it up, or how much would this block of metal? To be a bit more useful, we're going to look at specific heat capacity. So that's taking into account the material that you're dealing with. So how much energy does it take to heat up a certain material, like metal or copper or water, by 1 degree Celsius? And to make it a fair comparison, we look at how much energy it takes to raise 1 kilo of that material by 1 degree Celsius or Kelvin. So we just need to alter our equation a little bit here to take into account the fact that we're now multiplying by kilos. Same with the unit. The unit is joules per kilogram per Kelvin. And our kind of formula here now is the energy added or lost is equal to the mass in kilos, always make sure it's in kilos, times the specific heat capacity of the material, times the change in temperature. One quick caveat to add to that is that this is when the material is not changing state, but staying in the same state. So staying as a liquid or a solid or a gas. We're going to try a few examples now. And again, I'd like you to try each one yourself and then listen to my explanation and give it a whirl. Obviously, you'll get more confident with these as you go. So if you want to watch the first, that's fine. But as we go on, try them yourself. All right, let's give it a go. Okay, we just need to alter our formula a little bit now that we're dealing with specific heat capacity. We have to now take into account the fact that it's the mass of the object times its specific heat capacity times the change in temperature will give us the energy used. So for number 4, we know that the change in temperature is the final temperature of 80 minus the initial temperature of 12, which is 68 degrees Celsius, or we can just write it as 68 Kelvin, because 68 degrees Celsius is equal to 68 Kelvin. We know that the mass, they're not trying to trip us up, they're giving it to us in kgs, so it's 2 kilos. So we can just pop this into our formula straight away. So the energy is the mass of 2 kilos times the specific heat capacity of water, which we're given in the question, which is 4180 joules per kilogram per Kelvin. And that's times the temperature change we're looking for, which is 68 Kelvin. And that works out as 568480. And because we know we're looking for energy, it should be joules. So let's just check. Kilograms times kilograms to minus 1, they cancel each other out. And Kelvin to the minus 1 cancels out this Kelvin, leaving us with just joules. Okay, they've given us a relatively straightforward now. So how much heat energy is needed to raise the temperature of 12 kilograms of copper from 10 to 80 degrees Celsius. Okay, so we're given our mass is 12 kilos. The change in temperature we're looking for is the final temperature of 120 degrees Celsius minus the initial of 10, which is 110 degrees Celsius, or 110 Kelvin, which we're going to use. And the heat energy transferred, therefore, is the mass of 12 kilos times the specific heat capacity of copper, which is given in the question, which is 390 joules per kilogram per Kelvin. And again, that's multiplied by a temperature difference, which was 110 Kelvin, just about fitted in there. And multiply that out. 514,800 joules. And again, always check your units. Kilograms by kilograms to the minus 1 cancel each other out. Kelvin to the minus 1 times this Kelvin cancel each other out, leaving us with just joules, which is what we're looking for. Alright, in this one we're going to have to do a little bit of rearranging, but it's still quite straightforward. So this time we're given the energy that was transferred, which was 11,088 joules. And we know that the mass is 1.6 kilograms of copper. Okay, and let's start with our equation. Energy transferred is equal to the mass times the heat capacity times the delta Q by the change in temperature. Now we know from a previous question that the answer should be around 390 joules per kilogram per Kelvin. So that's kind of a good common sense check. If at the end our answer is close to 390, we've done well. Okay, so the Q is equal to M times C times delta theta. Let's get our change in temperature first. So that is from 25, which is our final, minus our initial, which is 7, which is 18 Celsius, or 18 Kelvin. And now let's just rearrange our formula a little bit. We start off with Q is equal to M times C times the change in temperature, but this time we're looking for the heat capacity. So let's divide Q by M and also by the change in temperature, which cancel out, leaving us with just the heat capacity. So that's 11088 joules divided by 1.6 kg times 18 Kelvin, which I worked out as 385. And let's pay attention to our units here. So it's, I know I've run out of room a little bit, just belly that up a little bit. So that's joules. We're dividing by kilograms, so it's kilogram minus 1. And we're dividing by Kelvin, which is Kelvin to the minus 1, which is the unit we use for specific heat capacity, so we're happy out. And 385 is pretty close to 390, so that seems like a... And the final one we're going to look at today is question 7. So they're trying to trip people a little bit, because they give 1 megajoule, but we now know that 1 megajoule is equal to 1 million joules. So we know our Q. And they're asking us to find the mass, but they've given us the heat capacity, and they say that the heat capacity is 451 joules per kilogram per Kelvin. And we're given the change in temperature as well. It started off at 20 and it went to 200, so the change is there for the final. 200 minus the initial, which is 180 degrees Celsius, or 180 Kelvin. So let's go back to our formula. We have Q is equal to MC times delta theta. Let's rearrange that, because this time we're looking for the mass. Let's get the mass on its own by dividing Q by the rest of it. So Q divided by the specific heat capacity times the change in temperature will give us our answer. So that's 1 million joules, which is the energy, divided by excuse me, the heat capacity, which was 451 joules per kilogram per Kelvin, which is multiplied by the temperature difference, which was 180 Kelvin. And that works out, I know you can't see, I'm just going to move up my screen a little bit here. It works out as 12.318, let's say, kilograms. Let's just check the units. Joules divided by joules, they're going to cancel out. Kilogram to the minus 1 is left here. And Kelvin to the minus 1 at the bottom times the other Kelvin, they cancel each other out as well, because K to the minus 1 times K is just gone, leaving some 12.3 kilograms of... Okay, we'll leave it there for today. You've done really well if you stayed with me so far. So here's a picture of some dogs wearing bandanas because I think they're cool. We're going to try some more challenging questions in the live class. So make sure you're comfortable with the ones I worked through. And if you'd like, have a go at the rest of the questions in exercise 15.1. It's on page 162 of your textbook. Those are the ones we're going to be going through in the live class. So have a go yourself. See how you get on. And we'll go through them together. All right, best of luck. Take her easy. Bye.